Hello everyone. Today we'll mainly learn about central limit theorem and you will see how for large number for any distribution we can apply central limit theorem and use normal distribution in that case. As I was saying, like the learning goal of this lesson is to know about the central limit theorem. We apply central limit theorem to know the sample mean distribution. So this is important to know, like we apply the central limit theorem to know the distribution of the sample mean. We'll elaborate on that later. And we can know the sample distribution when the population distribution is normal, and we can also know the distribution of the sample mean even when the population is not normal for other distribution, but in that case the sample size has to be at least 30. So this is important. So we can also apply central limit theorem even when the original distribution is not normal, but in that case the sample size has to be at least 30. So according to the central limit theorem, if x has a normal distribution with mean mu and a standard deviation sigma, then x bar, that mean the sample mean, right? X bar is the sample mean, also follow a normal distribution with the same mean and with a smaller standard deviation. We'll see like what is the standard deviation here. So here, let me repeat again. So if the original distribution is normal, if the original distribution of the population is normal with mean mu and a standard deviation sigma, then the distribution of the sample mean is also normal with the same mean and with a smaller standard deviation. So now let's see what we have. So here we have like the original distribution of x is normal distribution with mean mu and a standard deviation sigma, right? So x follows a normal distribution with mean mu and a standard deviation sigma. Then x bar, that means sample mean, right? X bar is the sample mean. Then x bar, that means sample mean, also follows a normal distribution with the same mean, right? Here we have mu, here as well we have the mu, and with a standard deviation sigma over square root of n. So earlier, like for the original distribution, we have the standard deviation sigma, but now in that case we have the standard deviation sigma over square root of n, where n is the sample size, right? So here the mean hasn't changed. So the for the sample mean, the mean is also mu, right? Like the original distribution, but the standard deviation of the sample mean is sigma over square root of n, right? Where n is the sample size. Let's look into an example here. So here for a particular pond, say we have trout fish, and the individual length of the trout fish is denoted by x, and x follows a normal distribution with mean mu, and mu is 10.2 inches here, and standard deviation sigma, which is 1.4 inches here, right? So I think it is clear to all of you about this example. We are interested for the length of trout fish in a pond, and the length of the trout fish follows a normal distribution with mean 10.2 inches and a standard deviation 1.4 inches, right? So now let's talk about two individual problems. So for the first problem, we are dealing with a single trout, and for the second problem, we are dealing with a sample of 5 trout, right? And our first question is finding the probability that a randomly selected trout length will fall in between 8 to 12 inches. And for the second question, our goal is to find the probability of mean length of 5 trout in between 8 to 12 inches, right? So for first one is the probability for an individual trout length, and second one is the probability of the mean of 5 trout length, right? And for the first one, we are interested to find like what is the probability that the individual length of a trout fish will fall in between 8 to 12 inches. And for the second problem, what is our problem here? So here, what is the probability that the mean length of 5 trout will fall in between 8 to 12 inches, right? So for the first one, we are dealing with an individual trout fish, and for the second problem, we are dealing with a sample of 5 trout, right? So we are already familiar with the first problem, right? So here we have to find what is the probability that x will fall in between 8 to 12 inches. So this is the raw x raw x value is 8 inches and 12 inches. So we have to find the corresponding G score, right? And the formula for the G score conversion is that, right? We already know that, like G equal to x minus mu over standard deviation. Then for the lower bound, what is the G score? For the lower bound, the G score would be the raw score here is 8, right? 8 inches. Then minus, this is the mean, and the mean was 10.2 over the standard deviation. Standard deviation in that case was 1.4, and the final value is negative 1.57. Similarly, for the upper bound, what is the G score? For the upper bound, for the G score, we have the raw score of 12, right? Here we have the 12 minus mean, which is 10.2, over standard deviation, which is 1.4, right? And this gives us the G score of 1.29. So I think it is clear to all of you, like we have already dealt with this kind of problem, right? So here we have the original score, and for the individual probability, since here we are dealing with the individual probability, so it is quite simple. The G score conversion is like that. We are already familiar with that, and we will use this formula to convert the raw score to the G score, right? And this is the value for the lower bound, and this is the value for the upper bound, right? In the previous slide, we have already discussed about like how we can calculate the G score for the lower bound and the upper bound. So now this is the probability in terms of the G score. So our original probability was, what is the probability that X will fall in between 8 and 12, right? So now we have converted this original problem into in terms of the G score, and now we are interested to know the probability that, what is the probability that G will be greater than negative 1.57 and less than 1.29, right? So that means we are interested for the probability of this area, right? We are interested to know this area. That means what is the area in between negative 1.57 to 1.29, right? Positive 1.29, this area. And in our normal distribution, during our normal distribution, we have discussed like how we can find this probability using the G-score table, right? I'll not be discussing that in details here, but here how we can find this area from this distribution. So we'll be using only the left G table. So that means we can know like the area, all the area that is below 1.29. That means we can know this area, right? So from this area, we have to subtract this area, right? So from this area to the left, from this area that's left to 1.29, we can subtract this area that is left to negative 1.57. And that give us the area in between negative 1.57 to 1.29, right? So that's what we have done. So here, then what we can do, so that is basically what is the probability that G score will be less than 1.29. What is the probability that G score will be less than 1.29? That means this area minus G score will be less than less than negative 1.57, right? Negative 1.57. So that means this area, and that will give us this probability. Now the area that is left to 1.29 is 0.9015. From the standard G table, we can get this area. I'll not discuss like how we can find this area, because I have already discussed that so many times in our previous 2 to 3 lessons, right? And now from that we have to subtract this area, and from the G table you can find this area, and the area is 0.0582, right? And that gives us the probability 0.8433. That means what would be the interpretation of that? The interpretation that the individual probability of trout length will fall that in between 8 to 12 inches is 0.84, right? That means about 84% probability that a single trout length will be in between 8 to 12 inches, right? I think now it is clear to all of you, right? We have already discussed how we can calculate probability for individual observation. And now we will see how for sample mean we can calculate the probability. And in our case, what is the sample size? Sample size is 5. We were interested to know the length of 5 trout, right? And the distribution was also a normal distribution with mean. The mean was same, right? The mean will be same according to central limit theory, and the mean was 10.2. And what would be the standard deviation? Standard deviation will change, right, for the sample mean, because now we are not dealing with individual trout. We are dealing with a sample of 5 trout, right? And we are dealing with sample mean in that case. And in that case, the standard deviation would be original standard deviation over a square root of sample size. And what was our original standard deviation? Standard deviation was 1.4 over square root of sample size, and in our case the sample size was 5. Therefore the standard deviation for the sample mean would be 0.626, right? So by applying the central limit theorem, we find this standard deviation. So standard deviation of the sample mean is basically known as standard error. So you should also know that. So this is also a standard deviation, but since we are dealing with the standard deviation of the sample mean, we also call that standard error. So let's discuss what is the difference between the first problem and the second problem. So the difference was, for the first problem we were dealing with an individual trout, and therefore in that case the standard deviation will not change, and the standard deviation was 1.4. And now for this problem we are dealing with a sample mean of 5 trout, right? And in that case the standard deviation will change, and the standard deviation in that case would be original standard deviation 1.4 over square root of sample size, and the sample size in that case was 5, and that give us the standard error of sample mean, right? So here this is different. This is very important to know. Like when we deal with the individual observation, then the standard deviation doesn't change, but when we deal with sample mean, then the standard deviation changes, and this is the change that will happen, right? So let me tell about the problem again. So here our problem was, what is the probability that the sample mean will fall in between 8 to 12 inches, right? And again for this and this one, like we also need to use the G conversion from the original raw score to the G score, and this is the formula that we'll be using here. And in that case we are dealing with sample mean, right? So here instead of X we have to use the sample mean, and here this is the distribution of the sample mean, right? This is the distribution of the sample mean. And so here is the mean of the sample, and this is the standard deviation of the sample, right? And what is the first score? What is the lower bound here? For in terms of raw score, it was 8. So from the 8 we have to convert to the G score, right? So 8 minus this is the mean, and standard deviation in that case will change, right? And the original distribution, the standard deviation was 1.4, but since we are now dealing with sample, therefore we have a reduced standard deviation, and we know this value is now 0.626, and we have already discussed like how it is 0.626, right? And the lower bound value then in terms of G score is negative 3.51. Similarly for the upper bound, the G score is in that case the raw score was 12, right? Raw score was 12. So from 12 minus this is the mean, this is the sample mean, right? And this is the standard deviation, and that give us the upper bound 2.87, right? So in that case now our lower bound for the sample mean is then negative 3.15, and for the upper bound the score is 2.87, right? So in the previous slide we have already know like how we have got the G score value, right? This is the lower G score value, and this is the upper G score value. And now we are interested to know the probability, that what would be the probability that G score will be in between negative 3.51 to 2.87, right? And we have already discussed like how we can find this probability. So here basically we need to find the area in between negative 3.51 and 2.87, right, from the standard normal distribution. And that means, like, we know what is the total area by using the left table, right, left G table, like what is the total area to the left side of 2.87, this area, and the area is like almost 1, right, since we have like very few area to the right side of 2.87. So the area is 0.9979, and then we have to subtract the area that is left side to negative 3.51, and that area is almost 0, which is like 0.0002. Therefore the final probability is 0.9979, right? So that means the probability that the mean length of 5 trout will fall in between 8 and 12 is 99.8%, right? And we can see like this probability is much higher than the individual probability that we have calculated earlier, which was about 84%, right? For a individual trout, we have already discussed that the mean length will fall in between 8 and 12 is with probability 84%. On the other hand, for a sample of size 5, the mean length will fall in between 8 and 12 is 99.8%. So what happens is that for an individual trout, sometimes the length could vary a lot, right? But when we deal with a sample, then even if like for some individual trout, the mean could vary, but the sample mean is consistent. And this is why in that case, we have higher probability that the mean length of 5 trout will fall in between 8 and 12 inches, 99.8%, right? And it would be greater, right? We can also present this information graphically. So here for the first case, for the individual trout, the length of a single trout will fall in between 8 to 12 is with probability 0.8433, right? And on the other hand, for the sample mean, that means for the mean length of the trout will fall in between 8 to 12 is with probability 0.9977, right? So here what happens, so for the individual trout, in that case the standard deviation was 1.4, but for the sample the standard deviation has reduced to 0.625, right? So it has reduced by like 1 over square root of 5, right? Reduced by this amount. And in that case the probability increases about 16%. So earlier the probability for the individual trout was like about 0.8484%, and in that case it is almost like 100%, right? So the probability in that case increases by about 16%. So far we have talked only about the normal distribution, but central limit theory can be applied for any other distribution which is not normal. But here the only thing that you have to remember is this central limit theory is only applicable for sample mean. We cannot use that for individual observation. And when the sample size is at least 30, then we can use central limit theorem. And central limit theory can be applied to any distribution. The distribution doesn't need to be symmetric. The distribution could be skewed, uniform, or any other distribution. So now this is important to remember. So if the population distribution is normal, then we can apply the central limit theory for any sample. So if the original distribution is normal, then we don't have to be like the sample size doesn't need to be like at least 30. So even for a smaller sample size, we can use the central limit theorem in that case. But when the population distribution is not normal, in that case, to apply the central limit theorem, our sample size has to be at least 30, right? And if the sample size is large, then the approximation gives us the better result. So that has to be remembered. So when the original distribution is normal, then we can directly use the central limit theorem. We don't have any restriction for the sample size. But when the population is not normal, in that case the sample size has to be at least 30, right? and the larger the sample size, the better the approximation. As we have already discussed, for any other distribution which is not normal, to apply the central limit theory, our sample size need to be at least 30, right? Sample size need to be at least 30. And then for the mean of x, what would be the mean of x? The mean of x would be like the mu, same as the original distribution, but the standard deviation would be like sigma over square root of n. So sigma was the standard deviation of the population, right? And in that case, now our standard deviation is reduced by, we have to divide that by square root of the sample size, where n is the sample size, right? So this is something that we have to remember. Let's now talk about this example. Suppose we are interested for the checkout time in the supermarket, and the checkout time, the distribution of this is not known to us, but we know the mean time. The mean time of the mean checkout time is 7.8 minute, with a standard deviation 1.5 minute, right? And the sample size we have is 40. So we are dealing with 40 shoppers, right? So this is the information that we have. So now the question we have is, like, for the single shopper, what is the probability that one shopper spends time in between 8 to 9 minutes? And the second question is, what is the probability that the mean time for 40 shoppers will be in between 8 to 9 minutes? Now, as we have discussed, like, the central limit theory is applicable only for the sample mean, but here for the first problem we are dealing with a single shopper, therefore it is not the mean, right? It is not the sample mean. Therefore, according to central limit theory, since the original distribution is not known, it is not a normal distribution, it is not a it is unknown distribution, right? We do not know the distribution. Therefore, in that case, we cannot apply the central limit theory, since we are dealing with an individual shopper, right? But on the other hand, since for the second case we are dealing with the sample mean, and in that case our sample size is 40, which is greater than 30, therefore in that case we can apply the central limit theorem, right? And we can answer this question, and we will see in the following slides like how we can do that. As I have said, like, we cannot solve the first problem, right? Why we cannot solve the first problem? Because we do not know the original distribution, and if we do not know the original distribution, then we cannot apply the central limit theorem for a single observation or for individual, right? This is why we cannot solve the problem number 1, but we can solve the problem number 2, right? And in that case our sample size was 40, which is greater than 30, right? And then the mean would be the same, right? And only thing that would be different is the standard deviation. And for the original distribution, the standard deviation was 1.5, and now therefore for the sample mean, the standard deviation would be 1.5 over a square root of the sample size, and in our case our sample size is 40. Therefore in that case the standard deviation is 0.237, right? And what would be the mean? The mean would be the same, and in that case the for the original distribution the mean was 7.8, and for this distribution, for the sample mean distribution of the sample mean, that would also be like 7.8, because the mean will not vary. And the standard deviation, now we will have a reduced standard deviation. Earlier the standard deviation was 1.5 for the population distribution. Now standard deviation of the sample mean would be 0.237, right? So now you already know the sample mean and the sample standard deviation for the sample mean, right? So now we can calculate the lower bound and the upper bound. So for the lower bound, what is the G score? So to calculate the G score, what was the raw value for the lower bound? For the lower bound, the raw score is 8. Therefore it is 8 minus the mean. What was the mean here? The mean was 7.8 over a standard deviation, right? And the standard deviation we have seen is 0.237, right? Therefore the final value for the lower bound in terms of G score is 0.84. Similarly for the upper bound, what is the upper bound value? Original value was 9, So it's 9 minus mean 7.8 over standard deviation, and the standard deviation of 0.237, right? Therefore the final value for the upper bound is 5.06, right? So in that case our lower bound value is 0.84 and the upper bound value is 5.04, right? So now in terms of GS score, this is the probability that we have to calculate. The probability that GS score will be greater than 0.84 and less than 5.06. And how we can calculate that, we already know that, right? So we have to basically, take the probability that GS score will be less than 5.06 minus probability that GS score would be less than 0.84, right? We already know that, so I'll not be discussing that again like in details, because we have already discussed that in our previous two modules, right? And then this probability is approximately 1 and this probability is 0.7995. Therefore the final probability 0.2005. That means about 20% chance that the mean checkout time for 40 shoppers is in between 8 to 9 minutes, right? So to summarize what we have learned in this lesson, so we have learned about the central limit theorem, right? And then we have discussed like we can directly apply the central limit theorem if we know the original distribution is normal. So for the normal distribution we don't have to worry about the sample size, we can directly apply the central limit theorem. But if the original distribution is not normal, then in that case to apply the central limit theorem our sample size has to be at least 30, right? And then we have also talked about a standard error. So what is the standard error? The standard deviation of the sample mean is known as a standard error, right? So what is a standard error? A standard error is the standard deviation of the sample mean, right?